Hi there. So we're going to spend this week talking about another type of equation. So we did parametric last week. This week we're going to talk about polar equations. And you're also going to have a review day to work through any remaining parts of any problem sets on Thursday. So you're basically going to have 2 work days this week instead of just Wednesday. So this video is going to be a little bit longer. You'll notice that this is a pretty big problem set. But these 2 topics, parametric and polar equations, are new. They're a little strange sometimes, and I want to give you that additional work time on Thursday. So again, we're going to talk about a different type of equation. So you're going to want to get your calculator out because once again, we are changing the mode here to polar. So get yourself ready for notes, get your calculator, and we're going to get started. Pause the video if you need to. So, polar equations, these are graphs that are created by rotating around the unit circle, and they're written in terms of r for radius and theta. So where theta is the angle around the unit circle and r is the radial length. So if you go to your calculator, you want to change the mode, make sure it's in radians. And make sure then if you want to change from parametric or function, these ones are going to be in polar. And what you're going to see then if you click on the y equals button, once you've changed these 2 modes as you need to in your calculator, if you go to the y equals button, you'll see here that you have r instead of an x and y as you would before. So the most basic type of polar equation is something like this, where it's just saying r equals 2. What this means is literally radius is equal to 2. And so if I type that in to my graph, you're going to get a circle with radius 2. So it goes through here, 2, 2, negative 2, negative 2. This is our most straightforward function, and as you watch it go around, it'll draw just the way I did, where it goes around the unit circle, starting here. If you kept going, it would keep going around, like so. If you want to recall conversions from x and y plane, if you remember from the unit circle, x is equal to the cosine of theta, and then just times r here for how far out you're going. So just cosine theta would be the unit circle. Radius will just tell us, oh, we maybe need to go a little bit farther than 1, such as that. And then y is r times the sine of theta at those points, because r will often be a function in terms of theta, such as we see here in number 1. Number 1 asks, sketch the graph r equals theta. Now, what I find easy here is one thing you can think about this as an ordered pair of r and theta. So this is the same as like x and equals y. So if you have r is equal to 0, theta is 0, pi over 2, since they're equal in this specific function. Pi, and so on. We can also convert those into an xy table using this function. Now, for the first one, r equals 0 all the way across. So x is equal to 0 times cosine of 0, which is 0. Y is equal to 0 times sine of 0, which is also 0. Here, pi over 2, we end up with pi over 2 is equal times cosine of pi over 2. If you remember, cosine of pi over 2 is 0. And here we have pi over 2 times sine of pi over 2, which is 1. Right here we would have negative pi, 0. If we kept going around, we'd have 0, 3 pi over 2, and then 2 pi, 0. So that when we're actually graphing on the xy plane, and you can check this on your calculator, you start at the point 0, 0. And then your next point is going to be at 0 pi over 2. So this is at about 1.5 here on the y-axis, treating these as ordered pairs like this. And if you graph it out, it's going to come around like this and form a little semicircle. Your next one is going to be at 0 pi over 2, negative pi 0. So this is at negative 3 here. Keeps going around. And you can check this on your calculator. It's going to keep forming an oval like this. Oop, that should have a negative. So sorry. And then this would be 2 pi. And what you'll notice is that when I say it's graphed as a rotation, we're going around the unit circle, and that radius is just getting bigger as it goes. So practice that you can graph these on your calculator, and then we're going to talk a little bit more about how to use them with your calculus ideas. So convert polar coordinates into rectangular coordinates. Again, you can use these functions. This will be a helpful thing to say, because what this tells us here is these are polar coordinates, so that means that they're in terms of r and theta, just as we see right here. So what this means is that r is equal to 4 and theta is equal to 2 pi over 3. So if I want to turn them into rectangular coordinates here, what that means is what are those in terms of x and y. And we can just use these functions here to convert. So what that says is that x is equal to 4 times cosine 2 pi over 3, and y equals 4 times sine of 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. If you want to use this as a fine opportunity to renew your memory of the unit circle, that's a lovely option. And then this would be 2 pi over 3 is positive 3 over 2. So in the unit circle, we're talking about this point right here, positive y, negative x. And therefore, our final answer, negative 2 for our x and 2 root 3 for our y. There's also, you want to be able to convert back and forth. So if we have the rectangular coordinates, the xy pair 2, 2, we can use these facts. So this is our general formula for a circle, x squared plus y squared equals r squared. So that allows us to solve for r. And if you remember on our unit circle, tangent of theta is equal to x over y, since y is sine of theta and x is cosine of theta. So what that'll let us do is convert these coordinates to 2. So we are going to say that 2 is our x and equal to our y. So 2 squared plus 2 squared is equal to r squared. And tangent of theta is equal to 2 over 2. Now here we have 8 is equal to r squared. So 2 root 2 is equal to r. Tangent of theta is equal to 1. And since we're in quadrant 1, theta is then pi over 4. Again, using our unit circle memories. And so then our final answer is 2 root 2 for r, pi over 4 for theta. Now, let's talk about how to use these in calculus. So, find the equation of the tangent line for r is equal to 1 plus sine of theta at theta equals pi over 3. So, since we want to find the tangent line, slope is still and always will be dy dx. So we're going to want to convert those in terms of the vocabulary of r and theta. So if you remember, y is, so instead of dy, we'd say it's the derivative of y in terms of theta over the derivative of x in terms of theta. Now, I will use our functions that we were just practicing. So then we've got r of theta as the function. And I'm just writing it like this so that you remember it's a function, it's not a constant, it does change. sine of theta, and x is r of theta times cosine of theta. And I've written it like this so that you remember you want to use the product rule. This is equal to the slope. So the product rule here is going to be r prime sine of theta plus r cosine of theta over r prime cosine of theta minus r sine of theta using that product rule. And so you can either remember this formula or you can rewrite it out. Either way, what we're going to do here is I'm going to use the formula. If r is equal to 1 plus sine of theta, then r prime is equal to cosine of theta. And so when I'm asked for the tangent line, I am going to start with the slope is equal to cosine of theta times sine of theta plus 1 plus sine theta times cosine theta for my numerator. And then r prime again, cosine of theta minus 1 plus sine theta sine theta. So one of the reasons I'm going to write it out like this first is often with our polar functions, you'll be able to use some of your trig rules to simplify the terms that we have here in case you want to. So in this case, we have cosine theta sine theta plus cosine theta plus cosine theta sine theta all over cosine squared theta minus sine theta minus sine squared theta. If we remember our formulas, and this is, again, a nice place to remember those. We have cosine squared theta minus sine squared theta minus sine theta. Unfortunately, we can't cancel this out with 1 or anything like that, but we can rewrite this to say, oh, well, this would be sine of 2 theta plus cosine, and this is cosine of 2 theta minus sine. So just a nice place to maybe practice some of our functions and formulae. From there, we're interested where this is pi over 3. So sine of 2 pi over 3 minus cosine of pi over 3 all over cosine of 2 pi over 3 minus, that should be plus, sorry about that, sine pi over 3 using our unit circle. 2 pi over 3, as we saw before, is here. Pi over 3 is right there. And that gives us sine values of root 3 over 2 plus 1/2 over negative 1/2 minus root 3 over 2. Now here's the nice thing with having simplified that all down. We have here both positive, same numbers but negative, so the slope is -1. And then we can plug it into our point slope formula. So y minus y1 is equal to m times x minus x1. Our y, we're going to use the function, and our x, we're going to use the functions here. So our x value is equal to 1 plus sine of pi over 3 times cosine pi over 3. Y is equal to 1 plus sine pi over 3 times sine pi over 3, which would be 1 plus root 3 over 2 times a half for x, and 1 plus root 3 over 2 times root 3 over 2 for y. You can plug that right in. I'm running out of space a little bit. If you want to see the full term, you can look at that on the notes if you want to see it all expanded out. I'm just going to use my calculator and write this as 1 minus 1.616 is equal to negative 1 times x minus 0.933. So, polar, more complicated than parametric, takes a little bit longer, but you're also not going to see a ton of these at any given time, so don't panic too much. For number 5, I'm going to cut this because I want to add in a note there, so if you don't have those written down, please do. Now for number 5, find the points of inflection. Now if you remember from before with parametric, our second derivative is equal to, in this case, d theta of our first derivative, all divided by our x derivative again. So it does become a very complicated piece to use our second derivative just like it is for parametric. Again, it's not like you're going to run into this a million times. And one nice thing is that you can definitely avoid using either of these complicated formulas if possible. And that's just to memorize the two basic shapes. Some of them you're going to just need to use your calculator, or you'll need to do a little practice. But I will tell you this right now, because this is one of those cases in number 5, 2 cosine of theta, is that you can just memorize anything that's a circle will look like either r is equal to a constant, and that's going to be just like what we saw before, where it's around the origin, where this is k. You also will have a circle if you have something times cosine of theta, and what that's going to look like is a circle on the x-axis here, where the diameter is k, and similarly, if you have k times sine of theta, that's going to be on the y-axis, again, where diameter is k, like that. So if you see something of this type, that's just going to be a circle. Now, for some of the more complicated ones, I recommend you use a calculator, do those things, but if you see these, it's a circle. And so if you're asked for, for an example here, find the inflection points, you can absolutely do the complicated mathematics. And I'll work through it because some of you said in the survey that you're interested in seeing more examples. But I would also point out, if I was asked this on a test, I would say, oh, well, I recognize this. This is a circle with cosine, so it's on the x-axis, with diameter 2. Find the inflection points here. Well, the inflection points, we have concave up in the lower half, and we have concave down in the upper half. So our two inflection points would by necessity be these two, which in terms of x and y, this point here, we've got 2, 0. Since it's between 0 and 2 pi, the radius is 2, and the angle measure would be 0 or 2 pi, since we think about the unit circle going around. The other point here has a radius of 0 and an angle of pi as we go around like so. You can use this. You can use your knowledge of these functions to get you there very easily. Since it's also where everything is equal to 0, this is also therefore when things are, whenever cosine is 0. So cosine is equal to 0, which would be also points 0, because the radius would be, let's see, pi over 2 and 3 pi over 2. So right now I've got all 1, 2, 3, 4, 5 inflection points that I want to test at this point, so I could jump straight to the number line and test my thetas at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I could jump straight to this point, testing for points of inflection. If I was on a multiple choice, I maybe am just going to make some assumptions. I'm looking at this point here and these ones here, which is in fact the correct answer. But let us go through our practice so that we have that example. But I just wanted to point out, you can memorize what these look like. You don't necessarily have to do calculus for all of these problems. But let's figure out what our second derivative would look like here. So the first thing I'm going to do is find dy dx is, and r prime is equal to -2 sine of theta. So here we have -2 sine theta times, I'll use my formulas right here so that you can follow along with me, times sine of theta plus 2 cosine theta all over r prime 2 sine theta times cosine theta minus 2 cosine theta sine theta. So the thing, I could jump straight to the second derivative here. That's going to be abominable. I'm going to see if I can simplify it any farther. One thing I do notice is that every single term has a 2 on it, so I'm just going to cancel that out right away. And I end up with negative sine squared plus cosine squared in the numerator, which is cosine of 2 theta. Here we have sine squared, cosine squared twice again, but it's negative, so this is negative sine of 2 theta. And I'll even simplify it farther to say that the first derivative is equal to negative cotangent of 2 theta. And this is going to be a lot easier now to find the second derivative, because I'm going to differentiate this and then divide by dx d theta, so this denominator again, which is -2, whoops, sorry. I could write it all out, but we already know it's negative sine of 2 theta from right here. So the derivative of negative cotangent of 2 theta is positive cosecant squared of 2 theta times 2 over excuse me, over, bring that 2 back in here that we canceled out. Whoop, forgot about that. -2 sine of 2 theta times 2. Cancel out the 2's, and I'm left with, I feel like I dropped a 2 based on my notes I have from before. If I did, I apologize. Let me check through this very quickly. That's why it's good to do both. But either way, we end up with negative 2 over sine squared of 2 theta. And remember, we're interested into where this is equal to 0 or where it does not exist for our answers. So it's never going to equal 0 because of the numerator, but we can look at where sine squared of 2 theta is equal to 0. So the question becomes, because that would be where it does not exist. Square root, we don't need to worry about the sine squared. And again, we end up with theta is equal to the same numbers as we have right here. And all we need to do then is test numbers on either side for r double prime. Well, not r double prime, but second derivative. Negative. And then it's 0 here, which is positive. 0 here, positive, negative, negative, positive. And remember, inflection points are just where it changes. So it changes once, twice, 3 times in that interval. So I know this is a longer video. You're going to have a work day, so feel that you at least have that extra space to work. Please be in touch if you're confused or have questions about anything that we've seen today.